Welcome to qnawire.
In this question, we are given the wave function of a particle or an electron defined by this wave function here. We're given the Schrodinger equation in terms of the x, y, z components of the particle's position, and we are also given, we're told to express the energy in this form here. So what we need to do is work out these differentials. So we'll start with the partial differential in x. So working out the first derivative, we see that deep psi over dx will simply be equal to, well, the only factor we need to really consider is this term with x in. So we end up with a kx, because the kx comes out. We get a cos kx x sine ky y sine kz z. When we take the second derivative of this, well, the differential of cos will be minus sine. So we can hopefully spot a trend here whereby we don't need to write out all of this expression all over again, because the second derivative will simply be minus kx squared, because the kx comes out, so we get a kx squared. However, we're left with a sine kxx again, which means that we have the original expression as before. So simply, it will just be equal to minus kx squared and then the original expression for psi. Now, because we have a wave function that's described in x, y, and z in the same way, we can simply say that the partial differential expressions for y and z will be analogous to that of x, as shown by these two here. So now we need to consider the boundary conditions of the particle. The first of which is that inside the box, no matter where you are inside the box, the potential energy of the particle will always equal 0. So all that simply means is that we can just cross off the u in this expression here. Secondly, in order to get in this expression in terms of number integers here, as well as the actual dimensions of the box itself, we need to look at what the value of psi will be at the walls of the box. So looking at, let's just say in the x direction, we know it's described by a sinusoidal relationship here. Now this could go on forever and ever if we wanted to, as far as L. But we know when x is 0 or L, so at the start or at the two walls of the box, the wave function must be equal 0, because you see these are infinite potential wells. We assume that the particles are confined to that box. We can't find them outside of the walls. Now, as such, let's write this out. So we know that sine, well, the x expression is sine k subscript x. Sine kxl must be equal to 0. So a sinusoid will be 0 when x is equal to 0, pi, 2 pi, 3 pi, etc. So integer multiples of pi. So as such, kx of L must be equal to an integer multiple, which we will call nx, multiplied by pi. And as such, we can then rearrange for kx to obtain this expression. Again, due to the nature of the wave function, the expression for kx will be analogous to those expressions for ky and kz, because the box has equal lengths in all dimensions. So therefore we can see that ky and kz will have the same expression for kx, with the only difference being that they are defined by their own unique integers ny and nz respectively. So now we need to substitute all of this information into the Schrodinger equation. Remember, we've already deduced that u must be 0. So we'll say that minus e is equal to, well, taking out common factors, we can say that minus e is equal to minus h bar squared pi squared, because remember we've got some k squared, kx, ky, and kz squared terms here, over 2, we're going to replace m, we're going to call it m subscript e, being the mass of the electron, multiplied by L squared, which again comes from our expression for k squared. And then all that's left is nx squared plus ny squared plus nz squared. And as we can see, the minus values will cancel, so we can just remove those. And that leaves us with the answer as required.